This is an example of an ECMO circuit. It consists of 4 primary constituent parts. Firstly, there's an access limb along which blood travels from the patient to the circuit. Secondly, there's a pump which on modern ECMO configurations is centrifugal in nature, and this generates the pressure differential to draw blood from the patient and through the circuit. Thirdly, there's a polymethyl pentane membrane oxygenator, and this is the point at which gas exchange occurs. The oxygenator is designed to provide a large surface area over which blood and fresh gas flow come in close proximity. Oxygen diffuses into the blood, carbon dioxide diffuses out. The fresh gas flow is introduced via the green tubing. The oxygenated and decarboxylated blood then passes via the return limb back to the patient. Other ancillary components of note are the pressure and flow monitors. These provide feedback on the performance of the circuit, and the heater-cooler unit, which maintains extracorporeal blood at a physiological temperature. When ECMO is used in the management of severe respiratory failure, it is usually in the veno-venous or VV configuration. That is, blood is drawn from the patient's venous circulation and is returned to the patient's venous circulation. Clearly, there must be an interface between the patient's venous system and the ECMO circuit, and that comes in the form of cannula. Various forms of ECMO cannulae are available. However, they are all large bore to allow the high blood flows required by ECMO, and they are inserted either via the jugular or femoral veins. This is an access cannula. It is multi-stage in nature, which means it has holes along the distal third of its length, and it is inserted into the femoral vein and advanced under fluoroscopy or ultrasound until the tip sits within the intrahepatic vena cava. This is a return cannula, which is inserted into the femoral vein and is advanced to the junction of the inferior vena cava and the right atrium. Regardless of the specific configuration, the principle is the same. Deoxygenated blood returning from the venous system is drawn into the ECMO circuit and oxygenated before being returned to the right atrium. From there, it is pumped into the pulmonary, then systemic circulations by the native heart. The circuit is controlled by a console. The operator manipulates the speed of the centrifugal pump, which, depending upon the many factors influencing the resistance of the circuit, will in turn influence blood flow within the circuit. Blood flow is the primary determinant of oxygenation in veno-venous ECMO, specifically blood flow as a proportion of cardiac output. The closer ECMO blood flow is to the cardiac output, the more deoxygenated blood returning from the venous system is oxygenated before entering the pulmonary, then systemic circulations. Carbon dioxide clearance, on the other hand, is determined by the flow of fresh gas through this membrane. The greater the fresh gas flow, the greater the carbon dioxide clearance.
We're gonna keep it low key, keep it softly spoken, with no strings tying you.